Good morning, everyone. We are from the mixed group at the University of Birmingham. Today, I'm going to present our work, Revisit the Open Nature of Open Vocabulary Semantic Segmentation. Semantic segmentation aims to assign a label to every pixel in an image. Traditional models work with a fixed label set, which we call the closed-word segmentation. However, in real-world applications, we often want models to recognize categories outside the training set. This is the Open Vocabulary Semantic Segmentation settings, which you can control the objects and categories you want to segment by giving any vocabularies as a query. However, the evaluation methods still rely on the intersection over unit, which we call the IOU, to evaluate model performance. But IOU only gives critics when the predicted label exactly matches the ground truth, which we believe is not suitable in the open world scenario. That means if a model predicts river instead of lake, even though they are semantically close, it's still penalized as a full error. To address this, some previous works propose using test similarity to assign partial credit for semantically close predictions. Instead of treating any mismatch as a full error, this method assigns partial credits if the predicted label is semantically similar to the ground truth. This gives a more reasonable evaluation, especially in the open vocabulary semantic segmentation settings, where the ambiguity is a common. Using test similarity to soften evaluation seems intuitive, but there's a challenge here. As shown here, different similarity measures produce very different similarity metrics. This means the evaluation outcome becomes highly dependent on the choice of similarity metric, which introduce inconsistency and make it hard to draw reliable conclusions. Instead, here we propose a mask-wise evaluation protocol based purely on visual overlap, like a child playing a shape matching game. If the predicted mask aligns well with the ground truth, like this, even if the labels differ slightly, we treat it as a meaningful match. However, here is a tricky situation. What if a predicted mask partially overlaps with a ground truth mask, meaning the shapes match to some extent, but the predicted label is completely different? As shown here, the green mask has a decent overlap with the triangle-shaped region, but it doesn't belong to the same category. It could be something like predicting river when the ground truth is tree. To address this issue, we apply threshold filtering strategy. We set a very high error threshold so that only predicting masks that are almost perfectly aligned with the ground truth are considered matched. Based on the high error matches between predicted masks and ground truth masks, we categorized each pair into one of the three types. The first one is the target pairs. There are pairs where the predicted mask naturally aligns with the corresponding ground truth masks. The second one is the error pairs. These are the predicted masks that mistakenly overlap with the wrong ground truth region or the mask. They are considered model errors. The third one is the matched pairs. There are pairs where the predicted mask overlaps well with the ground truth mask, but their category labels do not match. By separating matches in this way, we can better understand how the model is behaving, not just whether it gets the final answer right, but how and where to get it gets confused. Here's an overview of our entire framework. We start with the model's logics and generate binary masks by applying a confidence threshold. Next, we perform matching between the predicted and the ground truth masks, resulting in three types of the pairs. To better understand the model's behavior, we build an ambiguous vocabulary graph based on these relationships and perform community discovery to reveal clusters of confusing labels or the vocabularies. Here's the evaluating benchmarks. We apply our evaluation protocols on different kinds of the open vocabulary semantic segmentation methods. Interestingly, our evaluation protocol also gives us a new perspective on vocabulary. When we apply community discovery on the ambiguous vocabulary graph, we find that semantically similar or visually confusing labels naturally cluster together, like the road and the pavement. So in addition to evaluating performance, our protocol also reveals hidden semantic structures in the label space. Here's a visual example of what our ambiguous vocabulary graph reveals. We find that the categories models frequently confused, like the river, water, and sea, are not only semantically close, but also visually very similar. Even for humans, they are often hard to distinguish. To summarize, we propose a new evaluation protocol for open vocabulary semantic segmentation that focuses on mask alignment and label ambiguity. And through our analysis, we showed that many errors are not model failures, but because of the semantic overlap and the incomplete annotation of the dataset.